Okay, guys, so today we're going to talk about vectors a bit, and I want to start today with some motivation. So I'm going to show you guys a picture. So here, the picture. So our goals today are to learn what is a vector, what's a standard basis, what's a displacement vector, what do we mean by the zero vector, what operations can we do with vectors and how do we do them, and then finally we're going to end up with what's a unit vector. I want to start today though with what's the use of a vector. So looking at this picture here, we can see that there's a bunch of complicated BS going on. So this picture is of a big gray tripod here in the center. So the big gray tripod is kind of this thing here. So there's the top. We've got a supporting leg here. There's another one in the back, and there's one here down the front, right? So that's the tripod I'm talking about. That thing is called a vortex, but it doesn't really matter. So big old rescue tripod. And the point of this thing is to get this pulley here. So this right here in the center, this guy, that's a pulley. And there's a rope that's running up this way through the pulley and then down over the side of the bridge. So we use this in search and rescue to bring people who have hurt themselves at the bottoms of bridges up onto the bridge so we can get them to a helicopter or an ambulance or whatever. This is sometimes safer than hiking them up the hillsides on the side. So all of the vectors that are going on in this picture are a bit much. So I'm just going to talk about the kind of ones that I need to the most. There are a lot of vectors going on here. So I'm really talking about where is the head of the tripod, because that's going to be the thing that kind of causes problems. So the problems that I'm worried about when I rig a system like this are that it might flip over, right? Like this big tripod's kind of hanging out there. If it flips over and goes off the edge of the bridge, then that's going to be really bad for these two guys that happen to be standing inside the thing. It's going to be even worse for whoever's on the rope on the other side of it. So let me just outline a couple of vectors here. This is just why are we doing vectors, right? I don't need you to know how the system's rigged. I'm probably never going to show you this picture again. So looking at the top, right, of the tripod, I've got a rope pulling back across the bridge. I've got another one pulling down along this side of the bridge and another one pulling down along this side of the bridge. I've got the three legs. Those are acting actually in support, right? So I've put those vectors, I put these arrows kind of pushing down. But what those are actually providing for me is upward force, right? Each leg is pushing up on the top and the ropes are pulling down. Does that kind of make sense? Hope that makes sense. Then I've got here on the attached to the pulley, right? So there's a vector that's pulling from the top of the tripod down to the pulley itself. And that force is actually made of two other forces. One along, oops, you can't see green at all on this picture. One along the rope here. That's the kind of pull in side of the rope that's going through a pulley on the back of this truck. And then it's actually getting turned into a horizontal there. So there's actually a whole bunch of like changes going on back here. This is the pulley I'm talking about, by the way. So this red vector goes through that pulley and then gets kind of adjusted back this way along the bridge. That's what we actually pull on. But then the truck is pulling back this way, right? So we've got a whole bunch of kind of pulls going on, right? On this pulley, we've got sort of three, right? There's the truck providing some like pull backwards. We've got the rope that we're sending up through the pulley, that's pulling upwards. Then we've got the other one pulling backwards, right? So there's all sorts of forces going on here. You guys might recognize that what I'm basically drawing here is a free body diagram. That's why we're starting with vectors, because we use them to draw things like free body diagrams. This system isn't quite a free body diagram just because like things are moving, but it's the kind of analysis we use. So ultimately here you can see there's lots of funky arrows going on. What I'm really talking about is how hard am I pulling and which direction am I pulling it? And that's all that makes a vector. So I'm going to add that over here to our little definition. We're just going to say answer to question 1 is a vector is a magnitude, right? That's a how big, and a direction. This is a little bit, we'll get a better definition of this in linear algebra if you take that class. But for right now, I want you to know it's a magnitude and a direction, and that's good enough. So how hard are you pulling, and which direction are you pulling in? I'm going to go back to some of what we were talking about the other day with points. So I'm going to pull in a little Math 3D here. So this should hopefully be a slightly less busy picture, right? So my goal here is, you've seen this picture, right? This is us talking about the point 1, 2, 3, right? So I've got my orange point, it's at 1, 2, 3, that's up here. And that's 1 in the X, 2 in the Y, and 3 in the Z. And I sort of used these arrows to lie to you yesterday. So I said, okay, so these things are kind of just the directions of how you get there. That's really also me thinking, if I had to push an orange point that started at the origin up to where this orange point is now, how would I do it? Well, I might push it 1 over, 2 back, and 3 up, right? So that's exactly what we're kind of thinking about here, right? So I can think that a point is also, in some sense, a vector, and that vector is going to be the vector that ends at that same point. So I'm going to give this vector an orange hue to demonstrate to you that it's actually kind of the same thing as that point. So what do I mean by it's kind of the same thing? Well, it's different. So, sorry. I'm going to tend to treat these two things as though they're pretty interchangeable, and we're going to do that a lot. But I need you to know there's a slight difference. So a point is just a point in space, right? It's a dot. A vector is a magnitude and a direction. So in my case, what that vector is the kind of push that it would take to get from the origin up to the point 1, 2, 3, right? So there is a distinguishing feature here. Points we can't do operations with, vectors we can. We're going to want to do lots of physics in this class, right? As motivated by the kind of engineering thing I just showed you. So as we think about doing physics, we need to be able to do operations, right? We need to be able to think, okay, I have a position, I want a velocity, or I have a velocity, I want an acceleration, or I know the acceleration, I want to know the position, right? That kind of kinematic stuff is exactly what we're going to spend a fair bit of time in the beginning of the course developing, okay? So we're asking those similar questions to what we asked in Calc 1. We're just going to use a better tool to do it. And so our better tool is going to be vectors. So I want you to get that there's a distinguishing kind of feature between a point and a vector in the book. And when I'm writing, I'm going to do my level best to distinguish. Some books do this, some books don't. The book I'm currently using uses little Langle and Wrangle brackets. So they'd say 1, 2, 3 like this. This is a vector V. And we'd put our notation is going to be vector, so letter. Usually V, U, W are kind of common choices. Don't use X, Y, Z, please. I take it back about X. Then we put this little hat over the top. In the textbook, they're just bolded. On tests, they'll just be bolded, so you may have to look kind of closely. If you're not sure, ask. So I've got a vector V as distinguished from a point P, and a point P has round, so parentheses, as opposed to pointy guys. The pointy guys that we use here are not exactly the less than and greater symbols, which is why I'm going to call them Langle and Wrangle. Left angle, right angle. They're angle brackets, technically. Okay, so vectors look like this. Points have round brackets. And the distinguishing feature is going to be, am I talking about a magnitude and direction, or am I talking about a point? So this is a vector with a magnitude and a direction, and this is a point. And the difference is going to be, I can't do operations with points, but I can do operations with vectors. Okay, so that's my kind of answer to first question. Second question, what's the standard basis? Okay, so answer to second question. The standard basis is going to be I, J, and k, and these are going to be the vectors that do what we talk about. So when I'm looking at my, where'd my little guy go? This guy. Oh no, technology. Okay, so when we're talking about our vector here, right, we're saying we went 1 over, we went 2 in the y, and 3 in the z, right? So that I'm going to think over at that thing, right? So that's going to be kind of, I'm going to think right. So that's going to be the vector 1, 0, 0, right? 1 unit in the x direction. J is going to be 1 in the y direction, and z is going to be 1 up. Or sorry, k is going to be 1 up. So I've got I, j, and k. These are going to be our standard basis for 3 dimensions. Don't worry about what I mean by the word basis. You'll learn it in linear algebra. As far as what we mean here, we mean I is to the right, j is towards the positive y, k is up. Right? I keep screwing up j as saying forward or backwards, depending on which way I'm looking at the picture. So I'm going to just say towards the positive y. All right, so that's our kind of first 2 questions answered. All right, let's talk about a displacement vector. For that, I want to scroll down a little bit. I want to keep my goals. I'm going to keep this. Okay, so let's talk about a displacement vector. So here, here I'm going to snip a little bit of a picture. Come on. Okay, so I'm going to show you a more involved version of this sketch in a second, but for right now, I just want to snip a picture out of it. So here's my picture, right? This is of 2 points. I want to talk about going from the point A here to the point B. And so I need to talk about what kind of a force would it take to get me from A to B. If you're thinking this in your head, good, excellent work. Now I need to figure out how to actually do that, right? So we did a little bit of this by accident the other day. I really want to think, okay, I need to go over, I need to go back towards me, and then I need to go down. Okay, see that kind of setup? So we're gonna have to go kind of left towards us and down probably. So let's see if we can figure out a way to do that here. So here's a Math 3D sketch. I've got my 2 points. There, A is x1, y1, and z1, and B is x2, y2, and z2. So I'm hoping here that we can punch some stuff in and get a black vector that goes from A to B, right? So here's what I'm going to start that with. I'm going to start by saying, okay, let's see. If I need to go from A to B, that's 2 units to the left, it looks like, from this picture, right? So how did I get that? I took where B is, so that's going to be x2. Then you notice that's not quite far enough, right? Because it didn't start at A, it started at the origin. So I want to do subtract where x1 was. Okay, that looks like it's going 2 back, right? But it's starting at the origin, and that's not, yeah. Okay, so there's a thing about vectors. They're always kind of inherently based at the origin. If you want to base them somewhere else, you can do what's called a tailed vector or position shifted vector. So this guy here is pretty helpful to know how to do this. In Math 3D, you can just adjust the tail. So I want to put this at x1, comma, y1, comma, z1, because that's A. So normally this vector would be based at the origin, but because I'm illustrating something, I want to base it at A. So there it is based at A. So I can see that that actually does the X part. I'm hoping that you guys will see that the Y part ought to be done similarly, right? So the Y part ought to be Y2 minus Y1. Okay, so now we've That looks a little off, but I think it's just the perspective. Okay. And then our z component should be z2 minus z1. Hey, that's looking like the ticket. So that vector normally would look like this, right? So I'm just going to cut this guy and put in. Normally that vector would look like this because it's based at the origin. I don't really want it to be based at the origin because for illustrative purposes, I want it based up here. You guys see that? That tailing of the vector is kind of a thing that we're not going to worry about too much. It helps to know how to do it when you're drawing pictures, but it's not going to affect the math in like really, really meaningful ways. Okay, so that's my kind of displacement vector. And you might notice that we ended up using all the values for B as the first things, and then we use all the values for A as the second things. And what's really going on there is I'm kind of saying, okay, so to get from A to B, I'm going to treat A and B as vectors, and then I'm going to subtract the vector for A from the vector for B. So let me treat these guys as vectors quick. I'm just going to add another vector. This vector is actually going to be the vector that points at the point B. And we'll make this guy orange. Okay, so there we've got a vector pointing at the point B. I want to add another vector. And this one's going to be the one pointing at the point A. And we just need to get our values for the vector A out here. Okay, so I've got my vector A, my vector B, and then this black vector is the displacement vector, and that's the vector B minus A, right? The B vector minus A vector. We just subtract component wise. I haven't taught you to subtract yet, so what the hell? Let's do that next. Okay, so displacement vector. The thing I want you to remember from displacement vector is that it's terminal minus initial. And I just want you to think this, right? It's not quite a formula, but the formula, if I had to write it, would be the displacement vector from A to B is the vector B minus the vector A. All right, cool. Let's get a what's a zero vector out of the way. This one's going to be easy. The zero vector is the vector that's made out of, whoops, I just started writing a point. That's made out of zeros. We have a special symbol for this. We put a zero, and then we put a little vector hat on it. So zero with a vector hat on it. That's the zero vector. This seems like it's going to be really useless, but it's actually really kind of freaking important. So we give it its own name. In linear algebra, there will be one of you that will be appointed to be the keeper of the zero vector. And that'll be a thing you have to do all semester because it is really important to make sure you keep track of it. So here we'll have a bunch of uses for it, which is why I'm naming it today. Okay, let's talk operations. So operations are, I think, best illustrated kind of by dumb example. So here's a vector. I'm going to call this vector V. Here's another vector. We'll just go this way. I'm going to call this vector W. If I thought to myself, self, what if I did V and then W? Like, if I don't happen to notice that two vectors were applied, right, I might just see one result. You guys see this all the time when you kind of help a friend pull something across the ground, right? You're both pulling. You're pulling in slightly different directions. It doesn't actually matter. The result is kind of the same, right? It gets this kind of resulting vector. So our vector here is the vector v plus w, and that's the sum of the two forces, right? That's what happens when both things happen. It is worth noting that you can kind of rearrange this picture. I hope you guys see that I could rearrange this picture into doing v second and w first. So I'm just laying vectors tip to tail to figure out what the result is. You can do this with as many vectors as you want. This is the kind of pictorial vector addition. If you had vectors that were specifically written out, like say v was written out as x1, oops, what am I doing, Joe? Silly. So if v was x1, y1, and w was x2, y2, we could write v plus w is the new vector that's x1 plus x2 and y1 plus y2 here. And that'd be our new vector, right? We can see that this is commutative, and so it makes sense that the kind of picture should be commutative or the component-wise should be commutative. I am going to tend to call this component-wise. So that just means that I'm kind of thinking about the components themselves. You don't always have to do this with vectors. So if I tell you that you have to do something component-wise, you need to write it out this way. If I tell you, oh, you're doing that component-wise, you don't need to, then you probably think about it a little more abstractly without writing out all the little bits and bobs. Okay, so that's my kind of first operation. That's vector addition. Vector subtraction is kind of a weird one. Works the same way, actually, but I'm going to lump it in with this idea of scalar multiplication and then use vector addition afterwards. So let's talk about what is a scalar first. Okay, sorry, labeling's important. I'm going to try to do a good job of labeling. This is vector, this is 5a, vector addition. Okay, so this is going to be 5b, that's going to be scalar multiplication. So first things first, what is a scalar? What does the word scale mean? I know this is dead time in a video, it's kind of weird. So I'm giving you a chance to answer. So scalar multiplication is going to be multiplying by something that scales, right? So what scales? Well, I think about a vector as a force, right? It's got a magnitude and a direction. Well, if I don't change the direction, but I just make it longer or shorter, that's scaling it, right? So my kind of motivation here might be I might go back and think about my vector v that I had earlier, right? Got that vector v. If I add another vector v to it, I could look at this whole picture and kind of think to myself, well, self, that ought to be like two v's, right? V done back to back. Adding v plus v ought to give me 2v. And sure enough, the kind of result here, right, is that I get a vector that's scaled, right? It's twice as long. So that's the idea of scalar multiplication. So what does that mean? A scalar is? A scalar is just going to be a regular old number. So these are going to be multiplying vectors by regular ass numbers. Okay, so for right now, I want you to think of scalars as regular numbers. That's not going to go away. We're just going to have a slightly different definition later, but it'll come out to the same thing. So how do I do that? Well, picture-wise, I go like this. I go, okay, here's a vector v, and if I take and multiply that, right, I scale that by a vector. So I'm thinking I'm going to multiply it by a scalar a, right? I'm going to get a new vector that points in the same direction as v, but is now a times as long, right? So let's say this thing was, well, what the hell? In this case, you might be able to notice that from this picture, a is like 2.3-ish, right? Because this vector, my result av, is like 2.3 times the length of the vector I started with. So I want you to get, we're just scaling, right? This is basically pinch to zoom. Okay, So that's the kind of pictorial model. The component-wise model is pretty easy. Oops, I could spell component. Component. So component-wise, we're taking our vector v, right? V might be, say, x1, y1. And then we could say AV is going to be, well, they both need to get bigger or smaller as the value of A changes, right? So if A is 2, I double both of them. Yep, sure enough, same direction, right? It's parallel. You can figure out what the slope is by dividing the rise over the run or something. And we could notice that the A's would kind of cancel in that, right? So we'd get the same slope. And then when we think about how long it is, like, oh yeah, it seems like it got longer. I'm not really actually sure how to figure out how long things are, which is where we're kind of going to get into part C here. So C was magnitude. So I've been using the idea of, I've been saying, how long is a vector? Like, oh, it's this long. Like, oh, from this one to this one, it got 2.3 times longer. But what do I actually mean by magnitude? So the magnitude of a vector is the vector's length. Nothing else. Easy peasy, just like that. So if I'm talking about a vector, say here I've got a vector that I'm calling u, I want to know how long this vector is. Well, luckily, I've got some like tools. So I might do this. I might say, well, it went this far over, and then it went this far up, and there's like a Pythagorean thing for these. So if I'm like, okay, so let's say that our vector here is, I don't know, A in the X direction. So it's AI is the blue vector, and it's BJ, right? So I'm saying, what I'm saying here is I'm saying that my vector U, I could write it as A comma B, or I could write it as the vector A times I plus the vector B times J. Okay, so either of these is fine. This is the one that I kind of prefer that you use, but physics likes this kind of component-wise thing where you write out the I's and J's. So there are a bunch of these in the textbook. I encourage you to get good at switching back and forth. Sometimes it's easier to think one way than the other. So I've got my vector u. It's written these ways. I want to talk about the magnitude of u, right? So I'm slapping like double absolute value bars on this. That means the magnitude of u. Some books will only use one. That's fine. It's not going to hurt it. Right? And the way I calculate that magnitude is I take a and square it. I take b and square it. And then I square root the whole mess. Right? So that's me just literally applying the Pythagorean theorem. This happened in 2 dimensions. I encourage you to think for a second, what's going to be different in 3? Yeah, there's going to be a third component. That's it, nothing else. So that's magnitude. We've got component-wise scalar multiplication. I've got kind of the idea of scalar multiplication with pictures. I've got my vector addition. So let's go back to vector subtraction. How do you think vector subtraction works? So if I wanted to do something like, I'm going to call this D, even though we didn't say we were going to get a D. This is subtraction. So this is going to be, I want to take a vector V and subtract a vector W. Well, I'm really just going to rewrite that. I'm going to say that's the vector V plus, which is the operation that's actually defined, -1 times W. So picture-wise, I'm thinking I've got a vector V and a different vector W. If I want to do V minus W, I'm going to construct a backwards version of W, right? So here's minus W. And then I'm going to kind of tip to tail that with V, right? So I'm literally just going to pick that thing up and go, bam, right there. Oops. So that's my minus W here. And then my resulting vector is going to be this one. So it's going to start where V starts, and it's going to end where we ended with our tip to tail, right? So we took V first, and then we took minus W, and that ultimately brought us from where we started V out to where we ended minus W here. So that's our vector V minus W. And component-wise, let me tell you, this is super easy. You just subtract the components. You guys already knew that. I just wanted to draw a pretty picture. So that's what there is for operations. You might notice that if you multiply by the zero scalar, you're going to get the zero vector. And our last item is going to be, what's a unit vector? So a unit vector is a vector with length 1. So I'm starting with a vector. Let's say I'm going to start with a vector V. I'm going to give that thing a couple of components here. So that's going to be A and B, right? So I'm saying, here's a vector V. Now, I don't really know how long vector V is, but let's say it's a couple of units long. I'd like to scale it back. If it's 2 units long, I'd like to make it half as long. If it's 10 units long, I'd like to make it a tenth as long. If it's 2.3 units long, I'd like to make it 2.3 shorter, right, of its length. So I'd like to take it and divide its length by 2.3, I guess. So I'm going to say I've got a vector V, that's AB, a unit vector parallel to V. So I'm going to call this U. It's going to be a unit vector parallel to V. So I'm going to start with V. And then what I'd really like to do is slap a over here and then put down here how long V is. So that's the square root of A squared plus B squared. Now, this is our last like new thing. I want to introduce a new word. I'm going to type it. It's so important. So my new word is categorically. So what I mean by this is, maybe let me add an alternate use. So I'm going to ask you all the time, what category of thing is this? Like, okay, you've written this down. What kind of a thing is that? What I mean by that is it a number? Is it a vector? Is it a function? Is it a point in 3 space? Is it a 7-dimensional sphere? Is it a chair? Like, I don't give a shit. You just should know what things are. So when I'm looking at this, I've got a problem. So I'm looking at my what I've written down for U, which is, I think, the right idea. But something here is fishy, because right now what I've got written down for U is I've got on top, so categorically, and this is where I wanted to use the word. So categorically on the top here, this guy is a vector. Everybody on board with that? Okay. Down here on the bottom, I have a scalar. And I need to know, like, if I'm going to write these symbols down, I need to know that there is a way to sensically divide a vector by a scalar. So if I don't know that there's like a way that makes sense for those two operations to go together, I should probably do something else. So I need to know what I mean by this. I'm going to write what I mean by this really carefully here. What I actually mean by this, because I'm not like super satisfied with this notation, because I don't know really off the top of my head what it means to divide a vector by a scalar. What I want to do is I want to rewrite this as something I do know how to do. And something I do know how to do is I know how to take a scalar and divide it by a scalar. So here is now a scalar. And then I know how to multiply that by a vector. Get with me on that? So this operation that's happening right kind of in here is scalar multiplication. And that makes sense because I know how to do scalar multiplication, right? I showed you up here a component-wise way to do scalar multiplication. There's a bunch of rules for how scalar multiplication and vector addition interact. I want you to go find those in the book and see if you can convince yourself that they all make sense. There's 8 or so of them. They're well worth looking into. When we spend some more time in linear algebra, we're going to spend a lot more time with this. But for right now, I want you guys to have these kind of basics. So I'm hoping we hit everything here. If you have questions, feel free to hit me up in the Discord. Oops, wrong button. I don't know.